Hello, dear listeners. I would like to present my talk devoted to the temperature effects on luminescence of indium phosphide zinc sulfide quantum dots. It's a promising biocompatible material featuring size effect. Tunable optical properties of quantum dots make them advantageous in a variety of fields. However, there is still a lack of knowledge about non-radiative processes in the subject. Therefore, our work studies photo and thermally stimulated luminescence for two types of the quantum dots, denoted as QD1 and QD2. They have core shell structure coated with modified polyacrylic acid. According to dynamic light scattering, an average diameter and size distribution are smaller for the QD1. At room temperature, the samples have asymmetric emission bands. Upon temperature decreasing, intensity grows and spectral shoulders appear in the low energy region. For QD1, this feature turns to local maximum at low temperature. The high and low energy bands are assumed to originate from exciton and defect-related states correspondingly. Field thermal quenching was analyzed for the exciton and integrated intensity. Arrhenius plots demonstrate that the quenching processes are caused by the presence of at least two non-radiative relaxation pathways. Approximations by the mode relation with two channels give shown energy barriers. Comparing these graphs, we can see that the defect-related band affects PL quenching stronger in smaller QD1 nanocrystals. The quantum dots are found to exhibit thermally stimulated luminescence response upon heating after irradiation by deuterium lamp during 10 minutes at 6.5 Kelvin. 3D plots of spectrally resolved emission feature one peak for each sample. Intensity has its maximal values in the slightly different spectral regions and around 140 kelvins. Even at low temperature, after irradiation had been turned off, we've detected long-lasting afterglow effect. As you can see on the upper plots, it wasn't vanished during the subsequent heating. Spectral resolution allows us to conclude that recombination centers revealed in TSL experiment correspond to emission via defect-related states observed upon cooling in photoluminescence. Glow curves for the maxima spectral regions are shown on the bottom plots. To evaluate activation energy of the traps, low temperature interval of peaks have been analyzed with the initial rise method. Arrhenius plots yield the same energy values while 27 millielectron volts. It points to the common origin of the traps in the studied quantum dot ensembles. The main findings are presented on the slide. Thank you for listening.